session on temporal planning. We are going to have 3 talks today, and we're starting out with Andrew Coles with PDDL Plus, planning with events and linear processes.
Okay, thank you, Jay. So, just to give you an overview of the talk in one slide, we started with a standard forward chaining temporal planner. We use POPF, where in any given state you can choose to apply an instantaneous action, as in classical planning, or you can start a new durative action, or you can end a durative action which is currently executing. Now we took that and we added events and processes from PDDL Plus. Now the big difference between events and processes and actions is events and processes occur if their preconditions are satisfied. You can't control that. But the real interesting research challenge is what if those preconditions depend on continuously changing numeric variables. So if it's just that the process occurs if proposition P is true, then we can look at the state, and in states in which P is true, we can automatically start the process. But the challenge is, what if it depends on a variable V, and we know that V is being modified by some continuous numeric change? So here's a running example, just to start with a PDDL 2.1 derivative action model. Here we have one for switching on a phone, and we can switch on a phone if it's not on, and if we have some battery charge left in the phone. Whilst the phone is on, we add the fact on at the start, we delete it at the end, and then we have this continuous numeric effect syntax that we're going to decrease the battery charge by 1 unit per unit of time. So that's d battery by dt equals 1. We can have another durative action that has another continuous effect. In this case, it's traveling from somewhere in the countryside to somewhere in the city. And whilst we go to the city, we're going to increase the signal level on our phone, and at the end we're going to be in the city. Then you can take these two and we can use them to trigger an instantaneous action that says, okay, we've managed to make a phone call. And you have to switch on your phone so the phone's switched on, and you have to travel to the city so that you're at the city. And then once you have those conditions, and if you have some battery charge left, then you can make a phone call. So this is PDDL 2.1. There's nothing new here. We can solve this with one of our planners from 2010, the planner POPF. And the thing POPF does is essentially, we're still doing forward chaining planning as you would do in non-temporal planning, but there's 2 differences to a sort of standard planning approach. First of all is we have bounds on the values of numeric variables. So instead of knowing that V is precisely equal to 7, we know that V, for instance, might be in the range of 4 to 8. And this is, I'll show you where this comes from later on, but this is due to the fact that we have continuous numeric effects active now. And depending on the timing we give to actions, it depends on the variable, it influences the variable values we get. The other thing it does is it builds a partial order forwards. So instead of sequencing each step after the previous step, we have some rules which are based on essentially its strict emotion in partial order planning. So every time we add a fact, we note which plan step added that fact. And then every time we have a precondition on that fact, we order it after the most recent step that added that fact. And the same thing with numeric variables. Every time we have an effect on a variable, we order a precondition after all the effects on that variable in the plan so far. It's essentially so we still have a well-defined notion of a state, but we're not putting unnecessary ordering constraints into the plan. Now we get temporal constraints, these sequence constraints, but also because of the continuous numerics, we add those to the STP and we get a linear program. Where do they come from? Well, here's an example. The value of variable g at step j is equal to what it was after step I, plus the product of the gradient that's acting on the variable v times the distance in time between those 2 points. And this is why we are doing linear processes, because we have that delta v there and we're using a linear program. So that has to be a constant which we know at the time we're constructing the linear program. We can plug that in and solve it. So let's just quickly run through what that looks like. With some plan steps. So we apply our first plan step. That's going to switch on our phone, and it creates a variable which represents how much battery charge is in the phone, and it has a condition on it that is greater than 0. That's not particularly interesting, but as we build on that, we will refer to these variables later on. If we start traveling, again, we say, well, we have a signal level of 0, but we haven't necessarily moved yet, so we're not going to say anything beyond that. Where it starts to get interesting, if we end our traveling to the city action, well, we have to do several things. The first of all is we can now say that the signal level at point 2 in the plan is what it was at point 1 in the plan, plus 0.5 times the difference between those 2 time points. So they're sequenced, and we have some constraints on the distance between time points due to the durations of actions, and that implies what the values of the numeric variables are. So now we've switched on the phone and we've done the traveling, we can make our phone call, and to be able to make our phone call, we have constraints there which give us the value of the battery charge, and we can use those to make sure that the preconditions on those variables are satisfied. And if the LP doesn't have a solution, then it means at some point in this process, one of these preconditions wasn't actually satisfied. For instance, you didn't have enough battery charge, or your temporal constraints are inconsistent, as you would have in an STP. So none of this is new. So far, this is 2010 POPF work. Let's extend it with events and processes. So a process, it has a precondition. In this case, I'm going to have a process that my phone is going to start transferring data if I have enough signal and I have enough battery. And whilst those conditions are met and the phone switched on, I'm going to be transmitting data at a rate of 1 megabyte a second. Now, this might be a process I want to do. Maybe I want to check my email. Or it might be a process I don't want to do. Maybe I'm going out and I'm buying some flowers for my wife and she doesn't know, and I don't want any sort of location fix for me to be transmitted there. We can also have events. So an event occurs when its preconditions are met. Maybe we have an event which warns us that our phone is running low on charge. So when we have less than 8 battery and we haven't been warned yet, we will add the fact warned. And one of the things you get in PDDL Plus is that events have to violate one of their own preconditions, so they can't fire again, again, and again. So in this case, by adding the fact warned, that stops the event from triggering again in the next state, because we now no longer have the precondition not warned. The thing which really makes this interesting, though, which I mentioned right at the start, is signal and battery are subject to continuous numeric effects, because whilst we are traveling to the city, the signal level is changing. Whilst our phone is switched on, the battery level is changing. So if we actually want to ask the question, well, does this process happen? Well, if I fix the time points of switching on the phone and traveling to the city to 0, well, in that shaded region in the middle there, yes, the precondition is met. We have enough signal, but we haven't dropped below our battery charge yet. So yes, we do transfer data in that time. Or if we delay switching the phone on, then we can have an even longer period in which we're transmitting data, because the key thing is, if we delay switching the phone on, we delay the point at which we start consuming our battery, so we can have a longer period in which we can apply the process. Or if we delay setting off, so we stay at our initial location and just switch the phone on just to consume battery, we can then delay the point at which we set off, so there is no period in which the conditions of the process are true. Now, this is a headache from a planning point of view, because we have to plan actions around these processes, and we need to know what they're going to do, because what the processes do influences the soundness of our plan, and it also influences the preconditions of actions. So what we have to do to try and estimate the state in which we are in, for instance, in this case, we've switched the phone on and we've started traveling, we estimate the state we can be in by finding bounds on numeric variables. Now, we can only say that the battery charge is somewhere between 0.001 and 30. One case corresponds to we have switched the phone on and then waited for as long as possible, so that's the low battery case. And the 30 battery case corresponds to we've switched the phone on and we haven't allowed any time to pass between then and now. In the other case, similar idea with signal. Our minimum value of signal is if we delay starting our travel, because that increases signal. Our maximum value of signal is if we're going to start traveling and then allow a lot of time to pass, so we get a really great value of signal. You can note it's infinity because actually there's nothing there to stop it from escalating to infinity once this gradient is started. In reality, at some point, we would need to finish traveling to the city. That would actually place a cap on signal strength. But from this model, the key idea is we have bounds. So now we have bounds. Is this process actually going to happen? Well, let's generalize it. If we have these bounds, what can we say about a numeric condition? So in our state, we have bounds on variables, and our conditions are linear. So we're working with a linear program, so everything we express is linear. We have some weighted sum of variables is greater than or equal to some lower bound. Now, there are two easy cases. One is, regardless of the value of the variables we choose, we cannot make this condition satisfied. So if there's simply not enough battery or there's not enough fuel or whatever it is, we don't have to worry about this process because it cannot happen. Even if we have these optimistic bounds in the state, we simply cannot satisfy the condition on the process. Similarly, if we cannot unsatisfy the condition on the process, it has to happen. If there's no way we can consume enough battery, for instance, then a process requiring some level of battery will have to happen. Now, those are two easy cases because we can look at the state, we can say something about the process, we can add it to the model. The tricky case, though, is what if C could be true or false? So this is where the two key differences to our state progression start to come in compared to a PDDL 2.1 approach. So the two easy cases, we have a process with condition PI. If we can say we can definitely satisfy it or definitely can't unsatisfy it, then it can either has to happen or not. But in the tricky case, we're now actually going to introduce a planning step. So if you get to a state where you have a choice, at least it appears like you have a choice based on the numeric bounds, whether or not this process is going to happen, we have a planning step for that. And effectively, you can imagine it as two durative actions. We're going to have a durative action run PI, which has the condition of a process as it's an invariant, as its overall condition, and it has the effect of the process. So we can only apply that durative action if the condition of the process is actually met. On the other hand, we could choose to apply not run PI, which has the overall condition, which is the negation of the condition of the process, and it has no effects. So if we choose to apply that, we are asserting that we will ensure that the preconditions of the process are not satisfied, and therefore it's not going to happen. The key thing from a state progression point of view is starting one of these ends the other. You can switch from running the process to not running the process, but you can't have this indeterminate region in which you're neither committing to running it nor committing to not running it. So you end one action, you immediately start the other. And that's really important. I'll come on to that in a minute. For events, we can also start to think about them in terms of introducing extra choices. Again, we have the trivial cases where if the event's conditions are true, it has to fire. If the event's conditions cannot be true, it cannot fire. But again, if it could both fire or not, then we make a choice. If you like, our default position is to say, well, it's not firing, in which case we have a durative action, which has the overall condition, which is the negation of the condition of the event, and it has no effects. So that's saying, well, we are now going to choose as a planning step to make sure this event isn't going to happen. We can change our mind about that, again, as a planning step by saying, well, we can end this action do EJ, and then immediately we start it. And that's really important because at the start of the action, we have to have the condition of the event and the effects of the event occur. And then because once we've applied that, we've switched back to the overall condition, you can essentially see that we have punctuated regions in which the event's conditions do not hold due to the overall condition, with points at which the event's conditions do hold due to the start condition. So we can sort of reduce things down to durative actions. The question is, if we're doing that, did we actually need to start writing a new planner or doing anything vaguely sophisticated in the first place? Well, in principle, we can encode this in PDDL 2.1. You can compile PDDL plus down to PDDL 2.1. If you know epsilons, it's correct to within a few epsilons. If you don't know epsilons, you're incredibly fortunate. But this is detailed in the paper. The two key issues, though. One is, even these easy cases have to be planned. So these cases where you get to a state and say, hey, the condition on the process is satisfied, we have to start this process. That becomes an explicit planning step. And the second thing, which is perhaps even more of an issue, is this synchronization. I've said, well, somehow we have to ensure if we stop the process, we immediately start not doing the process. We have these pairs of actions, and you've got to make sure they're correctly synchronized. On the left, we have the case for the process, where if we're going to switch from not running our transfer process to running our transfer process, those two time points have to overlap there. We can't allow any time slip in between. On the right, we have our event case. Again, we can't allow any time slip. And if you don't want time slip in PDDL 2.1, you have to introduce extra dummy actions just to hold these points of the action together. And they have really nasty properties. It does terrible things to the search space. But the other complication, which means, in fact, looking at the state of the art, we did need to modify the planner all along, are disjunctive invariants. Now, POPF and our existing planners do not handle ADL. So as soon as we take a negation of a process's condition, even if it's a conjunction, we end up with a disjunction. So we have to say that one of the terms in that conjunction is false to guarantee the process isn't happening. What we used to do is say between any 2 points in the plan at which we modified the value of a variable. So if we have an effect on a variable v at 2 time points, we say, well, at both of those time points, we best check that this overall condition definitely holds. And that's sufficient, because in between those 2 points, we have linear monotonic change, so it suffices to check it at the boundaries of that interval. If we don't want this process to happen, though, this no longer holds. If we check at the start of this interval, is the negation of this condition true? Well, we can say, well, yes, because signal is less than or equal to 5 at the start, so the invariant holds there. At the end of the interval, battery is less than or equal to 10, so the invariant holds there. But you can see in the middle, there was a region where signal was actually greater than 5 and battery was actually greater than 10. So we actually have to modify the planner to be able to account for these. It's not as horrible as you might think. Because we've got linear monotonic change, we can actually exploit this. We can split regions between the points at which you check invariants. We can add extra dummy points. So if we have a disjunction which comprises n terms, we need to split the region between 2 actions which change the variable into n intervals. So here's an example of a condition, but either blue is greater than 10, or green is greater than 5, or red is greater than 5. We need to respect this disjunctive invariant across that interval. Well, on the first part of the graph on the left there, at the start of that, blue is greater than 10, and at the end of it, blue is greater than 10. So we've satisfied it for that region, but then we allow it to change which one of these it relies on for the next region. So green is greater than 5 at the start of the middle, and green is greater than 5 at the end of the middle, and so on. We can actually encode this as a mixed integer programming problem. So we're not introducing extra plan steps to deal with. We're just taking our LP model, we're raising the complexity of it, granted, by turning it into a MIP. But this is much more efficient than actually forcing the planner to do some Baroque compilation where you have to take a disjunctive condition and split it into several possible component derivative actions. And the key thing is, because we are doing linear monotonic change, this works. If we had non-monotonic change, we had changing points, for instance, we could no longer rely on this. So how do we evaluate this? Well, it's the first fully automated PDDL plus planner. We could compare to UP Murphy, but UP Murphy relies on a domain-dependent discretization, so we couldn't compare to that. So what we compared to was actually the necessity of making any of these changes I proposed in this talk at all, and just saying, let's compile it back down to PDDL 2.1 and use the planner you wrote 4 years ago. So we've got 3 domains with processes and events. The first is a variant of the planning competition satellite domain, where we have a process for sunrise and a process for sunset, and this controls the power availability of a satellite. We have a transformer domain, which is based on a power substation where you have fluctuating demand throughout the day, and you're needing to plan the substation actions in order to regulate that demand to meet the needs of consumers. The thing which makes it interesting from a PDDL plus point of view is we have events that fire if the voltage level goes out of range. So if the voltage on a line is more than 10% above nominal, then the insulation breaks down. In this case, it triggers an event, which is, again, it's governed by continuous numeric change, so we actually need to make sure that doesn't fire. The other domain we have is a variant of one we presented in ICAPS 2012 on the liner shipping fleet repositioning problem. And the thing we have here is a process that counts cost, because when a ship leaves its initial port and before it gets to its destination port, you've got to pay the wages for people on that ship, so you have a hotel cost. And predictably, it was a runaway success. It's somewhat unsatisfying as an evaluation, but the compilation can solve, I think, in total four or five problems across the benchmarks domains we had, whereas we could solve all of them, and we got some insights about scalability. In the transformer domain, you can see it's a zigzag line. The high points are winter demand, where it's really challenging. The lower points are summer demand, where it's relatively easy because people are using less power. This is in Britain. We don't have air conditioning, we have heating. So to conclude, we can take a forward chaining planning approach and we can extend it to region with PDDL+. There's lots of hidden details to do this. I've given you some of them in this talk. Do have a look at the paper. There's precise details of a PDDL 2.1 compilation in there if you want to read it and cry. The key detail is it's more efficient to actually modify the planner than it is to rely on the compilation in this case. And at the end of it, we've got the only fully automated linear PDDL plus planner. Thank you.
Questions?
So, while I have a newfound appreciation for the complications in temporal planning, let me see what happens if there's another one. So, for example, in the cell phone thing you showed, what if doing data transfer also increases the battery usage rate?
So, whilst the data is transferring so that would be fine. So the process which is transferring data would also decrease battery.
Right.
And you can have overlapping processes acting on the same numeric variable because it's linear, so it's additive. So
Okay.
as long as you know at the point at which you're building the LP what the gradient is, which you do because you sum it up, and then it goes up and down throughout the plan, you substitute that as a constant, you get the same LP as before. So.
Cool, thanks.
Oh, great work. I've got two questions. The first one is, do you have any intuition on how the linear monotonic change can be used for approximating nonlinear dynamics?
Sure. Okay, so...
and then, okay. Then the second one, do you have any intuition about the scalability of this planner in terms of the continuous change? So increasing the number of concurrent processes, for example.
Okay, so to answer your first question, so the thing which matters most to us is, in some senses, its monotonicity. If you have a function which can change directions, that disjunctive invariant trick goes out the window. We need linearity for an LP, but you could maybe look at relaxing that, maybe approximating it using a piecewise linear function. That's something we could explore. And your second question, in terms of scalability with number of numeric processes, it's actually pretty good. Because most of the time, in the benchmark problems we've looked at, most of the processes aren't happening. And you know they aren't happening. So you might have 100 ground process actions in your domain, but because we've modified the planner to have this sort of two-pass pruning of definitely satisfied and definitely unsatisfied, that eliminates all but a handful of the choice points at each state to make those manually decisions to switch processes on and off. But we could explore further pruning. There's definitely work to be done there.
Let's thank the speaker again.